We've already seen examples of both rational exponents and radicals, but in this section 7.5 we're going to learn some rules that we can use to link those together. So we're going to rewrite expressions that involve radicals and that involve rational exponents. See if we can go back and forth from one to the other. First definition here, we can use rational exponents to represent radicals. Again, I can go back and forth between the two. In a radical expression, the number a under the radical sign, which we have in this example here, is called the radicand, so that would be a in this example. Number n in the crook of the radical sign is the index, so if I see this radical sign and I have a number in there, that's what I call the index. Index gives the degree of the root. For a cube root, for example, you'd have a degree of 3, so I'd have a little 3 written in that crook. If there's no index, we have the degree 2, which means square root. So a square root, you don't need the 2 written in that crook. It'll mean a square root either way. So those three parts, again, index, radical sign, and radicand. And we've already seen some square roots before. So we've seen something, for example, like if 5 squared is 25, I can go the other way around and say that the square root of 25 is 5. And using that same idea, we also know that 25 raised to the 1/2 power is 5 for the same reason. Again, it takes 2 powers of 5 to make 25. So if we use that transitive property, I see that both of those are equal to 5. So we can also say square root of 25 is the same thing as writing 25 to the 1/2 power. And rather than just using square roots, it also works for cube roots and any other kind of root. If I take the cube root of 8, for example, which is 2, that's going to be the same as 8 raised to the 1/3 power, which is also 2. So it doesn't matter what index we use, that should still be similar from one to the other. We can simplify radical expressions by finding like factors, just as when we simplified our powers when we're using those rational exponents, so when we had those fractions as a power. So as some practice, we're going to find the simplified form of each of those expressions. We'll walk these through. And this is the cube root of 27. Remember before we thought what number is multiplied by itself 3 times to give you 27. And if you factor that down, so if I take 27 and think of some factors, 27 can be factored into 9 times 3. 9 can be factored further into 3 times 3. So if I'm trying to think what number is multiplied 3 times to get 27, we see that we have 3 3's, so 3 times 3 times 3 gives you 27. That means that number is going to be 3. So the cube root of 27 ends up being 3. Same type of question, if I'm looking for the fifth root of 32, I can factor 32 down first. So 4 times 8 would make 32. I can factor 4 as 2 times 2. 8 I can factor as 4 times 2, and 4 again I can factor as another 2 times 2. So this is one way to tell from your tree what number multiplied by itself 5 times gives you 32. That number is 2 because I see I have 1, 2, 3, 4, 5 factors that are all 2. Trying that again with a cube root of 64. 64, first of all, I can factor it into 8 times 8. And the 8's I can factor further into 4 times 2 and 4 times 2. So it's a little tricky here. We don't actually see one number being used 3 times, but what I can find is that if I'm using 4 twice, the other 2 powers here were 2. So 2 times 2 would make that last 4. So 4 times 4 and another 4, once I bring these 2's together, that means that number is 4. So again, 4 times 4 times 4, 4 multiplied by itself 3 times, that gives you 64. Last question here, we're looking for a square root of 36. Remember, we don't need to write the 2 in the radical sign. If I do, it still just means it's a square root, even if I left it out. So that's asking what number times itself gives you 36, and since I can factor that into 6 and 6, that means that that's going to be 6 as that simplified form. So if we want, in general, to find the nth root of a, and we're also using m as a power, I can write that a few different ways. I can write that as a to the 1 over n. So again, that's saying I can go from a rational exponent to a radical. And I can also use that as a power. So a to the m over n as a power means that the numerator is going to be your exponent and the denominator is going to be your index. So if I have m over n, if I have, so for example, 3 over 2, that would be a to the 3rd power inside of a square root. So we're going to try that here with some more practice. If I use a to the 5/6 power, I look to that numerator first, so the top of that fraction means that that's your exponent. A is being raised to the 5th power, and the denominator of that fraction, so the bottom, means that that's going to be your index. So a to the 5/6 means I take a, raise it to the 5th power, but I also have a 6th root. Next question, same idea. First thing we want to look for is that the 5 actually does not use that power of 1/3. I don't have exponents, or sorry, I don't have parentheses, so that means just the 5 is going to stay a 5. But since I'm taking x to the 1/3 power, x to the first is just x, so I don't really have any exponents that I need to write on the inside of that radical sign. But if I'm taking that to the 1/3 power, that means that that'll be a cube root. So 3, if it's on the bottom of that fraction, that means it's going to be your index. So last part of this is a little bit more challenging than the others, but if I have 54y raised to the 2/3 power, first difference from that last question is that since I'm using parentheses, that means that each part of that product is going to use that exponent. So 54 is raised to the 2/3 power, and also y is raised to the 2/3 power. And first of all, if I want to write those powers, again, the numerator is going to be the exponent. So 54 is raised to the second, y is also raised to the second, and the denominator is going to be the index or the root. So that will both be a cube root. And then if I want to factor that down, I wouldn't do 54 squared first. I would first try to factor 54. And since we're looking for a cube root, we're looking for what numbers can I look as a group of 3 when I break those factors down. So I'm looking for factors that comes in groups of 3. So 54 I can break into 27 times 2. I can factor that further into 9 times 3, and 9 would be 3 times 3. So what I see here, again, what we're looking for is groups of 3 for a factor. I have a group of 3 here, so I have 3 3s. That means I can take that outside of my radical sign. Since I'm still left with a 2, there's no group of 3 that I can use with a 2. That 2 is going to stay inside the radical sign. What we have to be careful of is that 54 was squared, so when I factor those out, if I factor the 3, I make sure that's still squared, and the 2 that I leave inside, I make sure that's still squared as well. With the y squared, we're not going to do anything with that because there's nothing I can do to simplify it. Last step is just to simplify. 3 squared would be 9, and 2 squared would be 4. So again, if you're looking to break those powers down, if I have 54, I want to factor it, and if I'm looking for a third root, I'm looking for groups of 3. So I have a group of 3 3s that I can factor out. The 2 stays in, and make sure we also use the numerator as a power, so 3 squared and 2 squared. So last practice is going back and forth from one form to another. This last practice we went from a rational exponent to a radical. Now we're going the other way, so from a radical to a exponent. And if I have s squared as a cube root, remember the numerator would be your power, so that would be your exponent. So I'd have 2 as a numerator, and your index is going to be your denominator, so that would be 2/3 power. Next question, 12 is not going to be using those powers because that's not inside that radical, so 12 is still just going to stay 12. And for the x, we have to remember it's the power over the index, so that's 4th power and third root. 4/3 would be your exponent. Next question is different from part B because this time the 4 is inside your radical sign. So 4 is going to be raised to the 5th power, and also y will be raised to the 5th power. What I also have to remember is that if it's inside a radical sign and if nothing's written in that index, that means that it's a square root. So it's to the 5th power with a square root. That means I can write that as 5/2 as a power. So again, it's the exponent over the index. And last question, if I take 256a to the 8th and I'm raising that to the 1/4 power because I'm using a 4th root, I just want to make sure here that everything stays on the inside of those parentheses because that stayed all together in that radical. And we could simplify this as well if we took the 4th root of 256 and if I took a to the 8th and I multiplied those powers as well. But if we're just going back from one form to another, let's just make sure that we can put that in exponent form first. So last question is using this concept with a word problem. We can estimate in this equation we're going to look for metabolism compared to body mass. So we're given a formula. R is going to be the metabolic rate, 73.3 is your coefficient, and then we have M with a 4th root and a 3rd power. So right away you might want to think what that would look like as an exponent. And in this question we're asked what's the metabolic rate of a man with a body mass of 75 kilograms. So basically all we have to do here is take that 75 and plug that in for M because that was the weight measured in kilograms. And when I do that, again, I can take that M, replace that with a 75 because I substituted our body mass. First thing that you can do is rewrite that radical as a rational exponent. Again, if I'm raising that to the third power, that's the numerator, and fourth root would be the denominator. And from there, you'd have to use your calculator. So if I multiplied 73.3 and 75 raised to the 3/4 power, that should come out to about 1,868 calories per day. So just make sure that you can go back and forth. If I take a radical, make sure you can write it as a rational exponent, and vice versa. If I start out with a rational exponent, make sure you can write it as a radical. It's the biggest idea, I think, to understand from 7.5, but we'll work on some questions in class.